But here we go. Hello.
Hey, how's it going?
Good. Let me turn you guys up a little bit. I need you guys to keep talking, though.
Okay. So we're looking at the black hole at the center of the galaxy again.
Sagittarius A star. All right. I think that's good. I can ask my chat. Wait, can you say something, Dr. Stefan?
Yeah, this is me.
Okay.
Hey, how's everybody doing? Let me, I'm gonna switch my sound real quick because then I can control the volume.
Awesome.
You can go ahead and keep going. This won't take long.
Okay, well, I'm going to bring up the images of some of the things that we're talking about, who we have on here too. I have linked this, guys, in the chat. We have Dr. Matthew Holman on here. You can go ahead and say hello.
Nice to meet you all.
And let me make sure. Go ahead and introduce yourself and talk about the first things that I like to know. First and foremost is kind of what got you into this in the first place with astronomy. I know you majored in mathematics from the get-go, but and you also got your degree, your first degree, your bachelor's in mathematics, but further on into the realm of astronomy and astrophysics.
Sure. Yeah. So I'm Matt Holman. I'm currently the director of the Minor Planet Center here at the Harvard-Smithsonian Center for Astrophysics. But as to how I got my start, so I always did math, since I was really young. It was sort of the continuous thing in my education. So it was sort of natural for me to keep doing that as an undergraduate. But I was always taking physics along the way. And I have a very good friend that I met in college, and he's a conductor now, an orchestral conductor, and he would be horrified to hear me say this, but he really had no business being at MIT, and he was doing his music, and he would often he was fascinated by astronomy, and he would say to me, "Why don't we take this astronomy class together?" Which sort of meant I would help him do his homework. And so along the way, I'd gotten lots of astronomy courses in, and we got pretty close to the end of undergraduate, and we needed to take a lab course. And there wasn't really a natural lab course in math, so I took this optical astronomy lab with this friend of mine, and I found out that I was really kind of a natural at it. It was really fun to do observational astronomy. And so I was getting to the point of applying to go to graduate school. I was applying to math programs, and this one, to stay at MIT for planetary science. And I happened to get in and decided at that point that I would just switch my path from being in math to doing planetary science. And despite kind of falling in love with observational astronomy, I did theoretical work in graduate school and continued doing theoretical work through postdocs and until I got the position I currently have at the observatory. And that was only when I got here that I had a chance to sort of scratch that itch to do observational astronomy. And so now I do a mix of both theoretical work and observational work.
Right, and you had. I'm sorry. Go ahead, Dr.
I do remember it was right around 2005 when you started doing the stuff with the Kepler cam to do the transit timing variations.
Yeah.
I remember you showing the picture, like this is a theorist getting back into or doing observational astronomy.
Yeah. It was great because I was doing a mix of photometry, measuring the light of from stars that have transiting planets, but I was also looking for Kuiper belt objects. And I'm still doing that. So I sort of early on, did this mix of observations of things in our solar system and observations and dynamics of things in our solar system and observations and dynamics of planets around other stars. So, it's been kind of a nice journey to get to do both.
And so, so moving to a lot of that stuff, your focus has been with these minor planets or smaller body, centaurs and discovering. I was looking at some of your stuff. Can you talk about what you found with not only Saturn, but Uranus and Neptune regarding some of the moons?
Yeah, so that was when I was working with a group of people looking for Kuiper belt objects. So Kuiper belt objects are things out beyond Neptune. And one of the people I was working with, Brett Gladman, had been on an observing run looking for Kuiper belt objects. And he had a little bit of extra time and was brainstorming to figure out what he would do. And he did this little search for moons around Uranus. And nobody had really conducted any kind of a big search for them since really the advent of big digital cameras. And he happened to find a couple of them. And as a group, we decided to sort of systematically start looking for moons around the giant planets. And it was using very much the same technique of looking for a moving object against a background of stationary stars. But what was different was that the way you would find a moon is you'd look near a planet, because that's where moons are, and you can search for the moon has to be moving with the planet because it's bound. So we really got into that and found dozens of irregular satellites. Those are the moons of these planets that go in all kinds of different orbital directions rather than just the equatorial plane of the planets. And we found not only are every one of the giant planets has a whole set of these moons, but they come in little dynamical families, groups of moons that have very similar orbits. And they're clearly the result of the collisional disruption of a larger progenitor body. So that was pretty cool to find out.
And you actually worked on a team where you actually have been known now for Uranus and Neptune discovering some of these irregular moons.
Oh yeah. And we, at the time we were doing those searches in real time at the telescope on Mauna Kea. So it was really great because it was just instant gratification. We would be looking all night long, and every once in a while we would find something that was moving right with the planet and had to be a moon.
Right, and we were just actually talking about Triton and how weird that is. One of how it actually goes around Neptune in the reverse order than most moons do.
Yeah.
And do you have? I'm just curious to know. Did you guys look at that closer? Was that something you? I know it's not in your. I mean, I'm curious to hear what you.
We have seen it. We didn't. We looked. That turns up in the searches, right? That's one thing that when you do these kinds of surveys, you kind of rediscover everything that's there to be discovered, right? And so we definitely run into the ones that have been discovered long ago. So yeah, that's one of the nice things about the work is you're sort of re-encountering old friends.
Hey man, I got a question. So what is it that studying these moon systems and even this like Kuiper belt objects in general, what do we learn from that? What do we learn from that in general?
Well, so Kuiper belt objects in particular, I'll talk about that, is we're trying to find evidence of all the processes of the formation of the solar system. And one of the kind of features of our solar system is it's remarkably cleaned out, right? Almost all of the material that was once in our forming solar system has been incorporated either into the sun or into a planet. So if you want to find clues to how the solar system formed, you have to find the debris. And the debris is really like stuff out beyond Neptune or stuff in the asteroid belt. These are the places that sort of still hold clues to the processes of formation. And so that's the motivation for studying in detail the Kuiper belt, because we've learned over the years that based on the detailed distribution of the orbits of these things and their sizes, we know that the giant planets must have moved around substantially during the process of planet formation. So, and that's just an example of the kind of things that have been learned from doing these sort of systematic studies. So, we've done the same thing with irregular satellites. There, we were really trying to answer the question of where did these things come from? And the issue was about one of capture. So you brought up, Skylias brought up Triton. It has this really odd orbit, and it's going the opposite way around. Its planet is all the other moons. So it's a retrograde orbit, but it's also a circular orbit, and that's really weird. And the working hypothesis there is that something, Pluto size, made a really close passage to Neptune, and through the interaction with Neptune and the sun, it gradually spiraled into this circular retrograde orbit. And the irregular satellites, presumably, the idea was thought that they formed in a very similar process. But
what's an irregular satellite?
Good question. So an irregular satellite, as opposed to a regular satellite. So regular satellites are moons that orbit in the equator plane of the planet and have nearly circular orbits. And they all have pretty much the same, they're orbiting in the same plane. So examples are what we call the Galilean satellites of Jupiter. Those are all regular moons. Irregular satellites have much more distant orbits. They don't stick in one plane. They go in all different directions. There are retrogrades and progrades, and that kind of distribution made us wonder, how did they get there? How did were they captured from somewhere outside? Were they formed there? And the tricky thing about capture is that if some kind of small body can begin to come in and make a temporary orbit around a planet, it can just as easily escape as it got in. But the irregular satellites that we see now, they're bound. They're not going anywhere. And the leading theory now is that all the irregular satellites were captured in the process of the giant planets moving around in a very jagged fashion while they were scattering other large planetesimals in the late stages of planet formation. And so imagine you have this whole cloud of planetesimals around, and something causes this planet to, scatters it with this planet, and it kind of just quickly moves, it changes its velocity. Suddenly, the planet can be moving in the same direction as a bunch of planetesimals. And at that point, when they're moving in the same direction, they can become gravitationally bound to that planet. So it's sort of a very kind of almost like a magic trick that, in the process of moving this, jostling this planet, it suddenly entrains a whole bunch of other material. So that's actually the leading hypothesis.
And what, I did have somebody actually talk to me about this. I'm getting echo right now, and I don't know why. But,
yeah, I'm sorry, I missed the first part of what you said.
Yeah, it's okay. I don't know why I'm getting so much echo, though. It's not, okay, it's better. So it seems as if, though, with the, like you're saying, there's major planet or major moons, not moonlets, but the Galilean moons that do follow these circular orbits and on a plane close to what we see demonstrated on a larger scale with the ecliptic and our planets orbiting on that plane. And then you get things like Pluto, for instance, that's 17 degrees inclined to the ecliptic. Mm-hmm. Someone asked the question, and I actually thought it was really good to bring up at this point too. And they said, would those exaggerated or eccentric orbits or the inclined orbits, would they eventually settle down to the ecliptic over a period of, probably billions of years?
No, they won't. I mean, they will. Those orbits, they vary quite a bit because they're far enough out from the planets that the sun is a big perturber, is an important perturber, just like for our own moon. So the orbits do vary quite a bit over time, but long before they were to become more circular, they are much more likely to collide with another irregular satellite. That region around the giant planets with all of these satellites moving in different directions is one of the most collisional environments we know of in the solar system. So it's not like a sci-fi movie where there's an asteroid belt with all things crashing into each other all the time. But on the timescale of the solar system, millions and billions of years, those satellites will be collisionally disrupted. They'll crash into each other. So that's the more likely outcome.
Yeah, that's something we talk about here a lot because we want to make sure that people understand that Hollywood does have a tendency to make things a lot more violent and chaotic than they really are. So let's talk about kind of and I do have an emote in here, an emoticon for poor Pluto, because everybody is very sensitive about Pluto now being a a dwarf planet. But can you kind of, because that is a minor planet now, and we have others that we know of. Can you talk about your work with that and any information you have on minor planets, since you are the director?
Yeah. So you mean in Pluto and dwarf planets in particular, or?
Yeah, I mean, yeah, and I would like to also hear, but that can come later. But I'll get in. I'll have another question about something else, but that's down the road. So so Pluto and
yeah, how do you find them, and from there, like, how do the minor planets that we're finding, how do they compare to Pluto? Well, and why did Pluto never deserve to be a planet in the first place?
Okay, so let me start with how do you find them. The way you find them is by taking a series of pictures, and in the past they were big glass photographic plates, and so you take a picture, you wait maybe an hour, take another picture, and the stars are in the background. Stars and galaxies are moving extremely slowly. You can't you can't detect their motion on timescales of you can see that on years for nearby stars. But you take a couple of pictures and you line up the stars. The stars are stationary. An asteroid will be moving along. If you take 2 or 3 pictures, you'll see it move. And that's really why it's called a minor planet, because a planet is a wanderer. And these are minor planets. And so what's interesting is it's not, the asteroid is moving, but also the Earth is moving. And it's actually the Earth's motion that has the more, is apparent. It's basically like as if you were in your car driving along the highway and you look out the window, the fence posts along the highway will appear to be going backwards. The trees behind those fence posts will appear to be moving backwards more slowly. The mountains in the background really won't appear to move very quickly. They'll pass through them over a course of time. So asteroids, you're sort of detecting them the same way. You're sort of taking a movie, and because the Earth is moving faster than the asteroids appear to be going backwards. And their rate of motion is a measure of how far they are from the Earth. So, and so Pluto moves, much more slowly. And so when it was discovered, using the very same technique that people look for asteroids, then using photographic plates, now using big digital cameras, you just take this series of pictures and you see this thing moving along. If it's moving slowly enough, it must be quite far away.
Right.
So that's kind of how you find the asteroids. I know the last question was, why did Pluto ever deserve to be a planet? Something like that. I think I can tell you, really, there's an interesting story there. That shortly after the discovery of Uranus and then Neptune, people had tracked the orbit of Neptune and noticed that its predicted position deviated, or its observed position deviated from its predicted positions by a certain amount. And just like the location of Neptune was predicted and Neptune was then discovered, people were predicting that there must be something else out in the outer solar system beyond Neptune that's tugging on Neptune's orbit and accounting for the variation between the predicted and observed position. So that's when people started predicting there's a planet X out there, and Percival Lowell commissioned a survey that was later carried out by Clyde Tombaugh to find this planet X. So they really believed that they were looking for something that was massive enough to account for apparent perturbations in the trajectory of Neptune. And so when they found Pluto, they thought they really had the thing. And it took some time to realize that Pluto was unlikely to be massive enough to account for the deviations in Neptune's orbit. And then in the 70s, when a moon of, when Charon was discovered orbiting Pluto, then that really allowed a precise estimate of the total mass of the Pluto-Charon system. And everybody knew then that it really is not, it's a much smaller object. So there's quite a bit of time between discovering this thing and believing it's, it's likely to account for the perturbations of Neptune, and then finding out in the 70s it really can't be that, and then in the process finding out it has a very exotic orbit. So I think it was really only in the the early 90s with the discovery of 1992 QB1 by Dave Jewett and Jane Liu that we really began to understand that there's a whole flock of small bodies out, well, not so small bodies, up to Pluto size objects out beyond Neptune. And Pluto's really just a large member of the whole distribution. So this whole process of understanding, where do we put Pluto into our understanding of the solar system, it's been a process. So I think, to be charitable, scientists, I think, adapt to these changing facts and changing information, and people are slower to change their view of things. I don't mean that to be negative, but I will observe that adults have a very difficult time with Pluto being a dwarf planet. Kids had no trouble at all.
Mm-hmm. Right. Yeah. I think it's because we were raised with it, so somehow we have to hold on to it. Right. And for me, I think it's pretty exciting because we find other objects that are, potentially even more massive, like Eris. And so when we have more of these objects, I personally get excited and think, well, okay, so we just have a new classification. There's something else.
Well, yeah, I think actually, Tombaugh found something to me even more fascinating than a solitary planet, right? He found this whole he found the first member of a whole distribution of objects that tells us a lot about our solar system. And right. It's just kind of this ongoing process of discovery.
Yeah, absolutely. And now we're finding, there's how many, to date, do we have these dwarf planet size objects? Do you have just an estimate number off the top of your head?
There are tens of those, really. And it really depends on if you stick with officialdom as to what is categorized as a dwarf planet. It's a very small number because they you really have to have a certain amount of evidence that the thing has a certain size and a certain mass. But there are really quite a few others that are very likely to be massive enough to be spherical under the gravity of their own self-gravity. So they're really quite big. They're Ceres size or bigger, and some of them get up to be Pluto size and possibly bigger. So it's really an interesting population out there.
What is it about? What are some of the unusual things that haven't been explained from the dwarf planets that we've observed?
Well, one of the things that it intrigues people the most is there's a population of objects that have very eccentric orbits. Okay, so that's not so unusual. Pluto has this very eccentric orbit, but there's a population that have very eccentric orbits and really never come very close to Neptune. So they seem to be kind of detached from the rest of the solar system. And Sedna is an example of that. And now teams of people have discovered 10 or 12 of these objects that have these very long, elongated, very distant orbits. And explaining how those got there has really been kind of a conundrum, and it's really sort of led to interesting hypotheses, including the Planet 9 hypothesis that there's another Neptune-sized object very far out in the solar system that would be explaining these unusual orbits.
Right. We've been talking about that too with Mike Brown's observations, and also his colleague. I wouldn't dare try to pronounce the name because I don't want to not be able to pronounce it.
How do you pronounce Constantine's last name?
Batigan.
That's what. Okay. That's what I thought.
So that's not too bad. I got Boyajian, so I think we're good. But yeah, so we've been talking about that, and I've had a lot of people that when I started talking about having you on here, they were curious as to your thoughts on Planet X, Planet 9. I don't like to call it the thing that the media totes. I think it's Nibiru or something. Usually that's indicative of just kind of they're going to YouTube and not learning quality information. But what are your thoughts on that?
Well, it's fascinating enough that I doing work about it to try to understand how it would affect the distributions of distant Kuiper belt objects. But really what intrigues me most is what observational evidence can we collect that would allow us to kind of precisely point in the direction to search for it. And I think that's the goal of Mike Brown, Constantine Batigan, and several other people to really try to understand not only is this a viable hypothesis, and I believe it is. I mean, I think we'll find out. That's the process of science, is to continue to test a hypothesis and see if you can find confirmatory evidence or evidence that refutes it. And so for me, it's intriguing enough and seems feasible enough that I'll commit my own research time to it. And I'm focusing on the things that I think where I can make a contribution that's maybe a little different from what other people have done. So I've looked at novel ways to place some kind of constraints on a massive object out there. So for example, one thing we did was to say, well, if there is this Neptune-sized body out there, we should see it. Just like people were making this prediction that there was something out beyond Neptune that was perturbing its orbit. We said, well, okay, if there's this extra planet out there, we should be able to see that in the precise measurements of Kuiper belt objects. So there are a number of Kuiper belt objects that have been observed for, believe it or not, 60 years. And you might think, how do we, the first one after Pluto was only discovered in 1992. How's that worked? There are archival observations of a number of bright, large Kuiper belt objects. And so the project was to say, okay, let's see if we can detect a difference in the precise trajectories of Kuiper belt objects with or without Planet 9, Planet X. And you get to do two things. One, we get to rule out big swaths of the sky and masses of such a planet that are just not consistent with the data at all. You can say if you put a planet there and it's more massive than this or closer than this, you would see it in the trajectories of the Kuiper belt objects, and we don't see that, so you can rule out those possibilities. And then there are other regions of sky where you can say, okay, this is where you can have that planet, and it can have a certain mass and a certain distance from us. So that's one project we did, and the other one is building on a really fascinating idea that a group in France came up with, and that's the idea that the Cassini spacecraft, until very recently, was orbiting around Saturn. And we've been in constant radio contact with Cassini for more than 10 years. And because we know the speed of light, you have this constant yardstick between a ground station on the Earth and the Cassini spacecraft. So you get to measure that distance very, very precisely. In fact, you get to measure it to a precision of something like 30 meters. Really quite remarkable that you get to lay out a yardstick that's good to 30 meters across that extent of the solar system. And so they made this point, okay, if there is such a planet out there, it should impose its gravity, it should be pulling on Saturn and should be, pulling more on Saturn than it is on the sun, and more than it's pulling on the Earth because it's relatively farther away. And that should show up in what they call the the radio range. And so that the range is basically measuring the distance between the Earth and the spacecraft. It should show up, and you can then use that information to test various hypotheses for a planet 9, planet X kind of object. And again, there are big regions of the sky that you can rule out and say, well, it can't be there, and you're left with, you know, a particular region where you could say, well, it's still a viable hypothesis there. So that's the kind of stuff that I'm interested in, as well as doing the sort of detailed dynamical calculations to try to understand, okay, what is it about this hypothetical planet that would be causing these distant objects that have their orbits that they do to be dynamically chaotic. That's the kind of stuff that I really love to get into.
Awesome. And so there is something else. So with some of the ways you observe these things, I've heard that you've been able to use the Pan-STAR 1 telescope that's on Haleakala in Maui, Hawaii, and that you've been able to find something pretty interesting. There's been some kind of news going on about this.
Well, there's been a lot of news over the last couple of years. So are you thinking about the interstellar object? Or
yeah, I've been trying to teach my chat how to say this. The Omuamua.
Omuamua, yeah. So so this idea of an interstellar object is not a new idea. It's been around for quite some time, and there have been predictions that we should see such an object coming from beyond the solar system. And the idea is this, that in the process of forming a solar system, and basically forming a solar system is as a byproduct of forming a star. You can sort of think of the planets and the asteroids and the other objects as kind of leftover debris of forming a star. And that process is kind of inefficient. A lot of stuff gets thrown off and ejected in the process. So if you sort of assume that every solar system is doing that in the process of forming, it's throwing out debris, that means that there should be debris streaming from stars toward other stars. You know, kind of there's just sort of this background of stuff. And if you do the calculation, I mean, the volume is quite great. So it's not like the sci-fi movie where there's all this stuff is streaming at you. But if you do the calculations, you should see that, you know, very occasionally something that is on a hyperbolic unbound orbit would pass through the solar system. And this recent discovery is really the first convincing case of an object that is on a hyperbolic, unbound, passing through the solar system orbit. And so that's really exciting. And it's the result of, so the Pan-STAR 1 telescope has a very large field of view camera. And one of its science goals is to look for asteroids, look for near-Earth asteroids in particular. But a byproduct of that, kind of constantly observing, taking these pictures and looking for the moving objects and reporting them to the Minor Planet Center, is that every once in a while you find something that is really quite unusual. And if you have such a telescope and such a big field of view, you really can do that sort of what I would call the needle in the haystack problem. You look and you still have some probability, because you're looking kind of everywhere almost all the time. You have a chance to see these very, very rare events. So that's obviously gotten a lot of attention, deservedly so. And I would have to think, and I don't think I'm the only one on this, that now that one has been convincingly discovered, they'll start turning up. It's something about the psychology of science and lots of things. Once you understand that it's feasible, then people start to pay attention to the things that are feasible. And so I would have to think that in the archival data and in the data in the near future, we'll start to see these more regularly. They can't be very, very common, or we would have seen it before this one. But I don't think that they're exceedingly rare, so that it takes years and years before you see another one.
What was the? You may have answered this. I was had to do something real quick. What was the evidence that suggested that this thing actually came from outside the solar system?
I was just going to ask that.
Yeah, so the evidence is that the orbit is not elliptical. It's not going orbiting periodically around the sun. The first thing is to say, well, most likely this came from the solar system. It's just we just need to think of the reason why it has a hyperbolic orbit. So it's not the first time that we've seen something with a hyperbolic orbit, but usually what we see when we see something with a hyperbolic orbit, we can trace it back, and we find it made a close approach to usually Saturn, and Saturn has given it a gravity boost and is throwing it out of the solar system just like a spacecraft. And that that has a particular direction of time that often there are comets coming from very distant in the Oort cloud, so they're almost unbound to begin with. They come through the solar system, and Jupiter kicks them out, and we see them on the outward journey on this now hyperbolic trajectory. So hyperbolic means not elliptical going around, but it's a one-shot deal. But in this case, you wind it back and you don't find that encounter with Jupiter or Saturn. And people have basically exhausted all the possibilities that they could come up with as to how you would explain the orbit of this object and have it come from our solar system. So there just doesn't, based on the orbit tracking, there's not it seems to be the persuasive argument that it's from another, it's interstellar, it's from another solar system.
And so are they going to continue using Pan-STARRS for these, I guess you could say, extrasolar objects that
yeah, the Pan-STARRS, so there's Pan-STARRS 1 and Pan-STARRS 2, and they will continue to carry out these kind of sky surveys. They're funded primarily to look for near-Earth asteroids, and so they're looking for all kinds of asteroids, mostly looking for things that might come near the Earth. They're reporting all of those data to the Minor Planet Center, and they will continue to monitor to see if they see additional interstellar objects. Definitely.
Yeah,
and they're use those data to find centaurs and irregular satellites and Kuiper belt objects. It's really quite a versatile thing, and it's really not the only one. It's sort of the beginning. It's one of a number of large surveys, but other big surveys like the Large Synoptic Survey Telescope are just over the horizon. So this kind of idea of doing this large scale monitoring of the sky is going to be an ongoing endeavor. And so we can expect to see not only interstellar objects, but we will continue to find things that surprise us. And it's a point I've made several times over the years that the evidence that we're still exploring our solar system is that kind of thing, right? Where every few years there's some kind of new Kuiper belt. Like we didn't understand like there was a Kuiper belt in 1992. Find the first one, and then you find different categories of Kuiper belt objects, things that are scattered, and you find these very distant ones. Often, when we find one of those objects, a single case, it has significantly changed our estimates of the mass of material out beyond Neptune. And that's still happening with, the Planet 9, Planet X. We're still at the point where there's a viable hypothesis that there's a Neptune mass object at hundreds of astronomical units from the sun. To me, that basically says we're still in an era of exploration of our solar system. And I think we will be for generations, really, because we just keep moving the bar of exploration. And that's what makes it really fun, is there's always something new to find. So the telescopes like Pan-STARRS are great because they're not so specific, right? They're looking for near-Earth asteroids, but it was designed to do a whole range of science. And so if you just kind of take very general data that it's good for lots of different things, and it facilitates all the kinds of amazing discoveries.
Right, and so some of the things that were I'm getting that echo again. Is everybody hearing that?
I'm not hearing it.
Okay, it's good. We're good. But the with this, for instance, I was calling it a comet for a while because I figured anything that would come out from this would have to have some kind of ice nitrogen, methane, ammonia, some kind of, I'm treating it what we would find mostly what we find with like Kuiper belt objects and comets or Oort Cloud type, space rocks. But they found out that this doesn't seem to have that. Did that kind of puzzle you, or is that something that...
It surprised me. I'm just like you. I expected it to be, I thought it would be very much like an Oort Cloud comet. I thought it was an Oort Cloud comet that we just hadn't recognized initially, how it got its orbit. I think that was a reasonable hypothesis to say, well, it's most likely this thing came from our solar system. And so I expected it to be like an Oort Cloud comet.
Right. And have they been able to pinpoint? I'm sorry, I didn't mean to cut you off, but I wanted to know if that actually did shock you too, or if that was just me, in my amateur brain.
I mean, it's definitely surprising, and it's definitely surprising that the thing is like this needle-like shape. I mean, it's really, it's really fascinating, and I don't know. I mean, there are and will be papers written about, how it got that. I mean, it's not the only one with a very extreme shape, but this one's really quite extreme.
Right. Looks
so
like an arrowhead.
That's amazing.
And so have we been able to pinpoint its origin in interstellar space based on the trajectory of it?
I don't think that's feasible. I mean, we will be able to know, in the direction that it came from, but it's not going to. We can't sort of take that trajectory and say, oh yeah, it came from that star, because the stars are moving too, and it's really an almost impossible task because we'll be able to track the orbit, but I don't think we would ever have the precision we would need to be able to localize, to be able to figure out which star it came from. It could have come from many, so I don't think we will be able to achieve that.
Right, and it's moving in and out of our solar system pretty quick. From what I read, it's going to be out of here by December, right?
There's still opportunities to observe, but it's getting fainter.
Awesome.
So I have a question about the pan-stars in general, because my understanding was that the Air Force actually was part of the funding for it. So can you talk a little bit about the national defense aspects of pan-stars?
Well, so the Air Force doesn't have anything to do with it now, but they did in the earlier stages. They were, I believe that they were interested in imaging, near Earth space. I mean, so they're interested in artificial satellites and that kind of thing. And I don't know the details, but they, were, intending to, the telescope is kind of a prototype and the military has developed, kind of satellite tracking stations, and that's an old endeavor. And so I think that they funded the construction initially, and then they're no longer part of it.
That's interesting because I thought that they were interested in it not for satellite tracking, but for looking at possible collisions in the future.
I don't know the detail. I mean, what I know is from the early, I've been part of pan-stars really from the beginning. Early on when the Air Force was involved, we would take the exposure, and if there was a satellite trail across the exposure, which wasn't a rare occurrence, those data would be redacted, and sort of redacted in a funny way. Like you put a black line over, electronically over it and say, it's not there, so I mean, there was a way of sort of making ambiguous, you really didn't know positionally where the satellite was, and it was a very noisy process of, there are lots of pickup sticks all over your image, stuff getting redacted. So it was, from my point of view, it was a very cumbersome process that none of us really understood. I don't even think the people who were actively involved, at any level, civilian or military, understood, why that was happening. Eventually, somebody, very sensible person, said, that's not helping anybody. And they're not keeping a secret. There was no secret to be kept that could not be observed with a neighboring telescope. There's nothing.
Oh, okay.
There wasn't.
You can always build another one nearby. So
you see another one nearby, and there is another one nearby, and there's not. So there's no. All that's a long-winded way of saying they were quite interested in art satellites.
Okay, so let me go back to. Let's pretend that my original idea had merit, which it apparently doesn't. That we were looking for Earth-crossing asteroids. What is it?
That's true. That's still happening. You're thinking they were. I mean, that was a scientific motivation and continues to be to find near-Earth asteroids.
So what are the issues like? So the Armageddon and the whatever the movies about asteroids crashing into the Earth. What are the actual dangers, and how does Pan-STARRS and like LSST fit into that?
Well, okay, so the danger is this, that these are asteroid impacts on the Earth are exceedingly rare, and I mean there's a distribution of sizes. I mean, we're getting hit all the time by very small objects that burn up in the atmosphere, and then less frequently something is big enough and maybe made out of rock or iron and makes it all the way to the ground. And then even more rarely than that, there's something that causes some perceptible damage, like there was the bolide, the sort of airburst over Chelyabinsk in Russia that caused significant damage. That was just a few years ago. And then less frequently than that, there are the things that cause the Tunguska impact that flattens a forest, or Meteor crater. And then there's the event that wiped out the dinosaurs 65 million years ago, and that's a 10-kilometer asteroid. If we get hit by a 1-kilometer asteroid, it's global catastrophe. And getting hit by 140 meter, 150 meter object is a kind of a continental devastation. So it's an issue of asymmetric risk, right? Where it's extremely unlikely that it's going to happen, but it causes massive devastation. So you would if you can spend a few tens of millions of dollars a year to ascertain, if there is such a risk, why not do it? And that's the argument. And so the Congress has mandated 2 goals, and there's a third one in the works. The first goal was to find 90% of the 1-kilometer diameter bodies, and that's been achieved. And then the next goal is to find 90% of the 140 meter diameter bodies that could potentially hazard, things that have orbits that could at some point intersect with the Earth. And that has not yet been achieved. So that goal, the 140 meter goal, is we're talking about the things that could cause continental devastation. That's what LSST and Pan-STARRS and space-based proposed spacecraft like NEOCAM that would look for near-Earth asteroids from space. That's the goal there, is to try to achieve that, to find 90% of those objects. And you say, well, why 90%? You can't. It's impossible or very difficult to find 100% and be sure that you found 100% of them. You can ascertain that you can estimate that you've reached 90%, and it's just about risk mitigation. To say, okay, well, let's just lower that risk as much as we can. So that's what's going on there.
Yeah, so we have about 10 minutes left. I want to keep it to an hour, not to go over the hour, and be respectful of your time. I do have 2 questions that were asked, and probably during certain times. If that's okay, Dr. Stefan, is there anything else that you had potentially?
No, I'm good.
Okay. I have one from someone in my chat that said, given that there are so many large ice objects in the Kuiper belt, are the planets in the belt constantly getting pelted by them? If so, what does this do to the composition of these planets? And if they aren't being pelted, why not?
They are being pelted on a very slow timescale, and you can see it with the New Horizons mission. Was able to measure the cratering rate on Pluto and Charon and other moons of Pluto, And so you see evidence of impacts on our own moon. You see evidence of impacts on every solar system object that does not have a process of renewing its surface. So we know that Pluto has over some areas, it has a process of renewing the surface, where you would see a lot more craters. Like on our moon, our own moon is saturated with craters. You see big ones and small ones inside of bigger ones, and so we know, you can estimate when most of those crater impacts happen. So it's, to answer the question, out in the Kuiper belt, yes, things are getting pelted. It's not like a raining rocks, but on a regular basis, smaller Kuiper belt objects are crashing into bigger ones.
Yeah, there's some theories that say that, that's how we kind of got some of the carbon-based elements that we have here on Earth, or that we have had impacts from comets.
Yeah, definitely, and that's one of the lines of evidence that we were hit by the asteroid that killed the dinosaurs, is this thin layer of iridium.
Right.
That is between the Cretaceous and Tertiary boundary. There's this thin layer that is globally distributed, and it is believed that came from the impactor. Right,
and that's what caused the nuclear winter.
It's just basically that it changed the atmosphere.
Right.
Enough that it was probably not so much the boom, the dinosaurs are dead. It completely disrupted the atmosphere and probably the vegetation cycle and killed them off that way.
Yeah, and that's what we talk about too, because I said, everybody says the asteroid killed the dinosaurs, and I said, slow down. We can actually find iridium in the soil, and we have a nice band where we can detect it, and it's right around that time. And so we go into that. That's very important to note, because that is a result. There was a question that says, this one actually was a really good one. Are there any planets to actually detect any Oort Cloud object, or any plans, I can't read from this angle. Are there any plans to detect any Oort Cloud objects? And if not, what would you have any idea of how long it would take humanity to develop technology that could find Oort Cloud objects?
I think humanity has the technology, and it's an interesting possibility that people are actively working on. And so you cannot see directly the light from an Oort Cloud object when it's out that far away, because the light travels from the sun out to the object, and the object intercepts a very small fraction. So it's 1 over distance squared. It reflects off the object and works its way back, 1 over r squared. So as you push an object farther away from the sun, and we're still observing from near the sun, it becomes exceedingly faint very quickly. So how do you see such a faint object? Well, the idea is very similar to transiting extrasolar planets. You watch a whole bunch of stars and wait for small objects to pass in front of those stars. And what's interesting is that if that happens, the light from the star doesn't just go, drop sharply and then come back up as the object, traverses its face. You see a wave pattern. It's a Fresnel pattern. So you see this, wavy signal, and that tells you something about the size of the object and how far it is away. That's called an occultation. So there are, active surveys and proposals to survey to look for, to do what's called a blind occultation. So rather than, because you can't predict when this is going to happen, you just monitor a whole bunch of stars at once, over a period of time, and look for these occultation events. And it's a challenge because you need to observe. So the measure is what we call star hours. How many stars times how many hours do we need to observe to see one event? And the answer is 10,000. So you can observe 1,000 stars for 10 hours, or you can observe, one or two stars for thousands and thousands of hours. And the only real solid result there is somebody used the Hubble Space Telescope. And when the Hubble Space Telescope is observing any object, it has fine guidance system. So it's got these photometers that are pointing at stars and using that to guide this spacecraft. And it's collecting data while it's happening. So you basically have one or two stars for thousands of hours, and there are one or two events. But we could find to find an Oort cloud object is really tough. You could find an inner Oort cloud object that's maybe 1,000 or 1,500 of. But even if we were to find Kuiper belt objects, what you can do with occultation techniques is to see things that are in the 1 kilometer size or 150 meter size. These are objects that would be impossible to detect in reflected sunlight. They're much, much too small.
Right.
But you could actually detect them in this occultation. So that's a great question. It's a fascinating subject.
It is.
Is this something that you're doing with TESS? Are you planning to do this with TESS?
Basically, there's a whole group of people that always ask whenever there's a spacecraft, "Hey, do you have a photometer on there?" And I was part of a mission proposal that wasn't selected to do. It's basically a very similar to the Kepler mission. Instead of monitoring 100, 150,000 stars, taking exposures every minute or two or 30 minutes, it would be doing 20 to 40 hertz photometry on many thousands.
Oh, so is the issue that the cadence is too wide?
The cadence, the event occurs. The cadence is too wide. The event is over in about a second, and so you need to have 20 to 40 hertz photometry. So you just, it's a different game to be doing photometry at that speed. But it is feasible, and there are missions that are there's a mission or a ground-based survey that's happening. Will happen in the next couple of years. Looking for those.
Yeah,
but it's a real challenge.
Someone asked about and I don't know what they're referencing. So forgive me, but could that new atom interferometer create a telescope where you could visualize Kuiper belt objects? I don't know which one they're talking about.
ALMA. There is ALMA data, but it's hard to only on the very largest things can we really see. We sort of know we have, except for New Horizons going right up to Pluto, the images of Pluto were quite limited, and that's still the case. But people have definitely applied interferometry to those objects.
There's actually a pretty good question because this is something I do talk about a lot when talking about astronomy in general. Are we the center of the Oort cloud, or is that too vain to think?
Are we at the center? The sun is at the center.
Yeah.
Most likely. Yeah. And there's but the galaxy matters a lot in that case, and so that we have this cloud of stuff, and what dictates the extent, what sets the edge of that, and that's where the gravity of the galaxy starts to take over, and so stars at that or Oort cloud objects at that outer fringe, are kind of evaporating away. So in some sense, our sun is at the center of it, but it's not the only thing that's controlling it. It's sort of the result of the interplay of our star and passing stars and the gravitational pull of the plane of the galaxy and the center of the galaxy. So we can pretend that we're in charge of that, but it's not entirely up to us.
Yeah.
I have one last question for me, at least, and that is, what evidence is there, or what evidence could you look for to find an Oort cloud or Kuiper belt around a different star?
Well, the most straightforward thing is to look for the dust that comes off of the collisions of Kuiper belt objects. So there's always a certain, just like we have the zodiacal dust in our asteroid belt that you see in infrared, there is the same kind of zodiacal dust that comes from asteroid belts and Oort clouds. I mean, asteroid belts and Kuiper belts around other stars. So we already know about that.
That's actually pretty interesting. I didn't even think about that. But I think
that's what you can kind of observe, because there's a lot of surface area in dust. I mean, it's sort of a weird thing, but if you're going to look for something glowing, It's actually all of that dust. And so that's, you see that our zodiacal cloud. That's a good example of that.
Actually, this is a really good question. I think it will be the last one, because I don't want to take up. I really want to respect your time. So, someone just said, what percentage ratio of mass, comets and stuff? I'm sure he's including asteroids in that too, and maybe we could say dwarf planets as well, compared to the mass of the planetary region, excluding the sun. Like, what's the ratio of mass?
Oh, it's extreme, right? Because you can think about Jupiter is 1/1000th the mass of the sun. The Earth is 1/300th mass of Jupiter, and it just goes on, down from there. It's an extremely small fraction. All of that other debris. I mean, basically, if there's a Neptune-sized planet out there, that's going to dominate the mass, right? Otherwise, everything else that's not in one of the planets we know about right now is a very small fraction of the rest. I mean, substantially less than an Earth mass is the estimates. That maybe there's a tenth of an Earth mass. Well, if you include in the Oort cloud, maybe there's an Earth mass of small material out there, but it's not it's part in 10 to the 5, 10 to the minus 5, 10 to the minus part in 10 to the 5, 10 to the 6.
Very interesting. There you go. Wow. Yeah. So I'm okay with wrapping it up. I don't see any more questions right now. But yeah, I wanted to thank you so much for your time and talking about this. This is super interesting, and been kind of prepping everybody for a while, because we have a lot of stuff just even in our own neck of the woods or our, solar system. That's super interesting, and it's good for people to know that we're still trying to figure out things here, and we don't even know, we're not even close to understanding just our own solar system. We're still working on that. That will be a work in progress for some time.
Well, thanks very much.
Yeah, thanks a lot, Matt.
Yeah.
It's really interesting.
All right. Well, have a wonderful holiday, and I'm going to let you guys go. Thank you again, Dr. Holman and Dr. Stefan. All right. Bye-bye.
Right. Thanks.
There you guys go. Amazing. That was awesome. Big kudos to Dr. Stefan for getting that set up and in place. It was awesome. Hopefully you guys like that. There was a lot of stuff